In computing, an image scanner often abbreviated to just scanner, although the term is ambiguous out of context. Is a device that optically scans images, printed text, handwriting, or an object, and converts it to a digital image. Commonly used in offices are variations of the desktop flatbed scanner where the document is placed on a glass window for scanning. Handheld scanners, where the device is moved by hand, have evolved from text scanning ones to 3D scanners used for industrial design, reverse engineering, test and measurement, orthotics, gaming and other applications. Mechanically driven scanners that move the document are typically used for large format documents, where a flatbed design would be impractical. Modern scanners typically use a charge-coupled device or a contact image sensor as the image sensor, whereas drum scanners, developed earlier and still used for the highest possible image quality, use a photomultiplier tube as the image sensor. A rotary scanner, used for high-speed document scanning, is a type of drum scanner that uses a CCD array instead of a photomultiplier. Non-contact planetary scanners essentially photograph delicate books and documents. All these scanners produce two-dimensional images of subjects that are usually flat, but sometimes solid. 3D scanners produce information on the three-dimensional structure of solid objects. Digital cameras can be used for the same purposes as dedicated scanners. When compared to a true scanner, a camera image is subject to a degree of distortion, reflections, shadows, low contrast, and blur due to camera shake. Resolution is sufficient for less demanding applications. Digital cameras offer advantages of speed, portability and non-contact digitizing of thick documents without damaging the book spine. As of 2010, scanning technologies were combining 3D scanners with digital cameras to create full-color, photorealistic 3D models of objects. In the biomedical research area, detection devices for DNA microarrays are called scanners as well. These scanners are high-resolution systems, similar to microscopes. The detection is done via CCD or a photomultiplier tube. History. Modern scanners are considered the successors of early telephotography and fax input devices. The pantograph was an early form of facsimile machine transmitting over normal telegraph lines developed by Giovanni Casely, used commercially in the 1860s. That was the first such device to enter practical service. It used electromagnets to drive and synchronize movement of pendulums at the source and the distant location, to scan and reproduce images. It could transmit handwriting, signatures, or drawings within an area of up to 150 x 100 mm. A Permilde Bellon's Bellinograph of 1913, scanned using a photocell and transmitted over ordinary phone lines, formed the basis for the AT&T wire photo service. In Europe, services similar to a wire photo were called a Bellino. It was used by news agencies from the 1920s to the mid-1990s, and consisted of a rotating drum with a single photo detector at a standard speed of 60 or 120 RPMs. They send a linear analog AM signal through standard telephone voice lines to receptors, which synchronously print the proportional intensity on special paper. Color photos were sent as three separated RGB filtered images consecutively, but only for special events due to transmission costs. Types: drum. Drum scanners capture image information with photomultiplier tubes, rather than the charge-coupled device arrays found in flatbed scanners and inexpensive film scanners. Reflective and transmissive originals are mounted on an acrylic cylinder, the scanner drum, which rotates at high speed while it passes the object being scanned in front of precision optics that deliver image information to the PMTs. Most modern color drum scanners use three matched PMTs, which red, blue, and green light, respectively. Light from the original artwork is split into separate red, blue, and green beams in the optical bench of the scanner. The drum scanner gets its name from the clear acrylic cylinder, the drum, on which the original artwork is mounted for scanning. Depending on size, it is possible to mount originals up to 20 inches x 28, but maximum size varies by manufacturer. One of the unique features of drum scanners is the ability to control sample area and aperture size independently. The sample size is the area that the scanner encoder reads to create an individual pixel. The aperture is the actual opening that allows light into the optical bench of the scanner. The ability to control aperture and sample size separately is particularly useful for smoothing film grain when scanning black and white and color negative originals. While drum scanners are capable of scanning both reflective and transmissive artwork, a good quality flatbed scanner can produce good scans from reflective artwork. As a result, drum scanners are rarely used to scan prints now that high-quality, inexpensive flatbed scanners are readily available. Film, however, is where drum scanners continue to be the tool of choice for high-end applications. Because film can be wet-mounted to the scanner drum and because of the exceptional sensitivity of the PMTs, drum scanners are capable of capturing very subtle details in film originals. The situation as of 2014 was that only a few companies continued to manufacture drum scanners. While prices of both new and used units dropped from the start of the 21st century, they were still much more costly than CCD flatbed and film scanners. Image quality produced by flatbed scanners had improved to the degree that the best ones were suitable for most graphic arts operations, and they replaced drum scanners in many cases as they were less expensive and faster. However, drum scanners with their superior resolution, color gradation, and value structure continue to be used for scanning images to be much enlarged, and for museum-quality archiving of photographs and print production of high-quality books and magazine advertisements. As second-hand drum scanners became more plentiful and less costly, many fine art photographers acquired them. Flatbed, CCD scanner. A flatbed scanner is usually composed of a glass pane, under which there is a bright light which illuminates the pane, and a moving optical array in CCD scanning. CCD-type scanners typically contain 3 rows of sensors with red, green, and blue filters. CIS scanner. Contact image sensor scanning consists of a moving set of red, green and blue LEDs strobed for illumination and a connected monochromatic photodiode array under a rod lens array for light collection. Images to be scanned are placed face down on the glass, an opaque cover is lowered over it to exclude ambient light, and the sensor array and light source move across the pane, reading the entire area. An image is therefore visible to the detector only because of the light it reflects. Transparent images do not work in this way, and require special accessories that illuminate them from the upper side. Many scanners offer this as an option. Film. Slide, or negative film can be scanned in equipment specially manufactured for this purpose. Usually, uncut film strips of up to 6 frames, or 4 mounted slides, are inserted in a carrier, which is moved by a stepper motor across a lens and CCD sensor inside the scanner. Some models are mainly used for same-size scans. Film scanners vary a great deal in price and quality. Consumer scanners are relatively inexpensive while the most expensive professional CCD-based film scanning system was around $120,000. More expensive solutions are said to produce better results. Roller scanner. Scanners are available that pull a flat sheet over the scanning element between rotating rollers. They can only handle single sheets up to a specified width, but can be very compact, just requiring a pair of narrow rollers between which the document is passed. Some are portable, powered by batteries and with their own storage, eventually transferring stored scans to a computer over a USB or other interface. 3D scanner. 3D scanners collect data on the 3-dimensional shape and appearance of an object. Planetary scanner. Planetary scanners scan a delicate object without physical contact. Hand. Hand scanners are moved over the subject to be imaged by hand. There are 2 different types, document and 3D scanners. Hand document scanner. Handheld document scanners are manual devices that are dragged across the surface of the image to be scanned by hand. Scanning documents in this manner requires a steady hand, as an uneven scanning rate produces distorted images. An indicator light on the scanner indicates if motion is too fast. They typically have a start button, which is held by the user for the duration of the scan. Some switches to set the optical resolution. And a roller. which generates a clock pulse for synchronization with the computer. Older hand scanners were monochrome, and produced light from an array of green LEDs to illuminate the image. Later ones scan in monochrome or color, as desired. A hand scanner may have a small window through which the document being scanned could be viewed. In the early 1990s, many hand scanners had a proprietary interface module specific to a particular type of computer, such as an Atari ST or Commodore Amiga. Since the introduction of the USB standard, it is the interface most commonly used. Inexpensive portable battery-powered glide-over hand scanners, typically capable of scanning an area as wide as a normal letter and much longer, remain available as of 2014. Hand 3D scanner. Handheld 3D scanners are used in industrial design, reverse engineering, inspection and analysis, digital manufacturing and medical applications. To compensate for the uneven motion of the human hand, most 3D scanning systems rely on the placement of reference markers, typically adhesive reflective tabs that the scanner uses to align elements and mark positions in space. Portable image scanners are usually used in conjunction with a computer which controls the scanner and stores scans. Small portable scanners, either roller-fed or glide-over hand-operated, operated by batteries and with storage capability, are available for use away from a computer. Stored scans can be transferred later. Many can scan both small documents such as business cards until receipts, and letter-sized documents. Smartphone scanner apps. The higher resolution cameras fitted to some smartphones can produce reasonable quality document scans by taking a photograph with the phone's camera and post-processing it with a scanning app, a range of which are available for most phone operating systems, to whiten the background of a page, correct perspective distortion so that the shape of a rectangular document is corrected, convert to black and white, etc. Many such apps can scan multiple page documents with successive camera exposures and output them either as a single file or multiple page files. Some smartphone scanning apps can save documents directly to online storage locations, such as Dropbox and Evernote, send via email or fax documents via email to fax gateways. Smartphone scanner apps can be broadly divided into three categories. 1. Document scanning apps primarily designed to handle documents and output PDF, and sometimes JPEG, files. 2. Photo scanning apps that output JPEG files, and have editing functions useful for photo rather than document editing. And 3. Barcode-like QR code scanning apps that then search the Internet for information associated with the code. Image quality. Color scanners typically read RGB data from the array. This data is then processed with some proprietary algorithm to correct for different exposure conditions, and sent to the computer via the device's input-outputs interface. Color depth varies depending on the scanning array characteristics, but is usually at least 24 bits. High-quality models have 36 to 48 bits of color depth. Another qualifying parameter for a scanner is its resolution, measured in pixels per inch, sometimes more accurately referred to as samples per inch. Instead of using the scanner's true optical resolution, the only meaningful parameter, manufacturers like to refer to the interpolated resolution, which is much higher thanks to software interpolation. As of 2009, a high-end flatbed scanner can scan up to 5400 ppi and drum scanners have an optical resolution of between 3000 and 24,000 ppi. Manufacturers often claim interpolated resolutions as high as 19,200 ppi. But such numbers carry little meaningful value, because the number of possible interpolated pixels is unlimited and doing so does not increase the level of captured detail. The size of the file created increases with the square of the resolution. Doubling the resolution quadruples the file size. A resolution must be chosen that is within the capabilities of the equipment, preserves sufficient detail, and does not produce a file of excessive size. The file size can be reduced for a given resolution by using lossy compression methods such as JPEG, at some cost in quality. If the best possible quality is required, lossless compression should be used. Reduced quality files of smaller size can be produced from such an image when required. Purity can be diminished by scanner noise, optical flare, poor analog-to-digital conversion, scratches, dust, Newton's rings, out-of-focus sensors, improper scanner operation, and poor software. Drum scanners are said to produce the purest digital representations of the film, followed by high-end film scanners that use the larger Kodak trilinear sensors. The third important parameter for a scanner is its density range or range. A high-density range means that the scanner is able to record shadow details and brightness details in one scan. Density of film is measured on a base 10 log scale and varies between 0.0 and 4.0, about 13 stops. The maximum density of negative film is up to 3.0 D, while slide film can reach 4.0 D. Slower film can reach higher density than faster film. Consumer-level flatbed scanners have a range in the 2.5-3.0 range, adequate for negative film. High-end flatbed scanners can reach a range of 3.7. Drum scanners have a range of 3.6-4.5. By combining full-color imagery with 3D models, modern handheld scanners are able to completely reproduce objects electronically. The addition of 3D color printers enables accurate miniaturization of these objects, with applications across many industries and professions. Computer connection: scans must virtually always be transferred from the scanner to a computer or information storage system for further processing or storage. There are two basic issues: how the scanner is physically connected to the computer and how the application retrieves the information from the scanner. Direct physical connection to a computer: the file size of a scan can be up to about 100 megabytes for a 600 dpi 23x28 cm uncompressed 24-bit image. Scan files must be transferred and stored. Scanners can generate this volume of data in a matter of seconds, making a fast connection desirable. Scanners communicate to their host computer using one of the following physical interfaces, listing roughly from slow to fast. Parallel port: connecting through a parallel port is the slowest common transfer method. Early scanners had parallel port connections that could not transfer data faster than 70 kilobytes per second. The primary advantage of the parallel port connection was economic and user skill level. It avoided adding an interface card to the computer. GPIB, General Purpose Interface Bus. Certain drum scanners like the Howtech D4000 featured both SCSI and GPIB interface. The latter conforms to the IEEE 488 standard, introduced in the mid-Euro unregistered trademark 70s. The GPIB interface has only been used by a few scanner manufacturers, mostly serving the DOS Windows environment. For Apple Macintosh systems, National Instruments provided a new bus GPIB interface card. Small Computer System Interface, rarely used since the early 21st century, supported only by computers with a SCSI interface on a card or built-in. During the evolution of the SCSI standard, speeds increased. Widely available and easily set up USB and FireWire largely supplanted SCSI. Universal Serial Bus scanners can transfer data quickly. The early USB 1.1 standard could transfer data at 1.5 megabytes per second, but the later USB 2.0/3.0 standards can transfer at more than 20/60 megabytes per second in practice. FireWire, or IEEE 1394, is an interface of comparable speed to USB 2.0. Possible FireWire speeds are 25, 50, and 100. 400 and 800 megabits per second, but devices may not support all speeds. Proprietary interfaces were used on some early scanners that used a proprietary interface card rather than a standard interface. Indirect connection to a computer: during the early 1990s, professional flatbed scanners which were available over a local computer network. This proved useful to publishers, print shops, etc. This functionality largely fell out of use as the cost of flatbed scanners reduced enough to make sharing unnecessary. From 2000, all-in-one multi-purpose devices became available which were suitable for both small offices and consumers, with printing, scanning, copying, and fax capability in a single apparatus which can be made available to all members of a work group. There are also scanner sharing software available on the Internet. Battery-powered portable scanners store scans on internal memory. They can later be transferred to a computer either by direct connection, typically USB, or in some cases a memory card may be removed from the scanner and plugged into the computer. Applications Programming Interface. A paint application such as GIMP or Adobe Photoshop must communicate with the scanner. There are many different scanners, and many of those scanners use different protocols. In order to simplify applications programming, some applications programming interfaces were developed. The API presents a uniform interface to the scanner. This means that the application does not need to know the specific details of the scanner in order to access it directly. For example, Adobe Photoshop supports the Twain standard. Therefore, in theory, Photoshop can acquire an image from any scanner that has a Twain driver. In practice, there are often problems with an application communicating with a scanner. Either the application or the scanner manufacturer may have faults in their implementation of the API. Typically, the API is implemented as a dynamically linked library. Each scanner manufacturer provides software that translates the API procedure calls into primitive commands that are issued to a hardware controller. The manufacturer's part of the API is commonly called a device driver, but that designation is not strictly accurate. The API does not run in kernel mode and does not directly access the device. Rather, the scanner API library translates application requests into hardware requests. Common Scanner Software API Interfaces, SANE is a free open-source API for accessing scanners. Originally developed for Unix and Linux operating systems, it has been ported to OS/2, Mac OS X, and Microsoft Windows. Unlike Twain, SANE does not handle the user interface. This allows batch scans and transparent network access without any special support from the device driver. Twain is used by most scanners. Originally used for low-end and home use equipment, it is now widely used for large volume scanning. ISIS, created by Pixel Translations, which still uses SCSII for performance reasons, is used by large, departmental scale, machines. WIA is an API provided by Microsoft for use on Microsoft Windows. Bundled applications. Although no software beyond a scanning utility is a feature of any scanner, many scanners come bundled with software. Typically, in addition to the scanning utility, some type of image editing application, and optical character recognition software is supplied. OCR software converts graphical images of text into standard text that can be edited using common word processing and text editing software. Accuracy is rarely perfect. Output data. The scanned result is a non-compressed RGB image, which can be transferred to a computer's memory. Some scanners compress and clean up the image using embedded firmware. Once on the computer, the image can be processed with the raster graphics program and saved on a storage device. Images are usually stored on a hard disk. Pictures are normally stored in image formats such as uncompressed bitmap, non-lossy compressed TIFF and PNG, and lossy compressed JPEG. Documents are best stored in TIFF or PDF format. JPEG is particularly unsuitable for text. Optical character recognition software allows a scanned image of text to be converted into editable text with reasonable accuracy, so long as the text is cleanly printed and in a typeface and size that can be read by the software. OCR capability may be integrated into the scanning software, or the scanned image file can be processed with a separate OCR program. Document processing. The scanning or digitization of paper documents for storage makes different requirements of the scanning equipment used than scanning of pictures for reproduction. While documents can be scanned on general-purpose scanners, it is more efficiently performed on dedicated document scanners. When scanning large quantities of documents, speed and paper handling is very important, but the resolution of the scan will normally be much lower than for good reproduction of pictures. Document scanners have document feeders, usually larger than those sometimes found on copiers or all-purpose scanners. Scans are made at high speed, perhaps 20 to 150 pages per minute, often in grayscale, although many scanners support color. Many scanners can scan both sides of double-sided originals. Sophisticated document scanners have firmware or software that cleans up scans of text as they are produced, eliminating accidental marks and sharpening type. This would be unacceptable for photographic work, where marks cannot reliably be distinguished from desired fine detail. Files created are compressed as they are made. The resolution used is usually from 150 to 300 dpi, although the hardware may be capable of somewhat higher resolution. This produces images of text good enough to read and for optical character recognition, without the higher demands on storage space required by higher resolution images. Document scans are often processed using OCR technology to create editable and searchable files. Most scanners use ISIS or Twain device drivers to scan documents into TIFF format so that the scan pages can be fed into a document management system that will handle the archiving and retrieval of the scan pages. Lossy JPEG compression, which is very efficient for pictures, is undesirable for text documents, as slanted straight edges take on a jagged appearance, and solid black text on a light background compresses well with lossless compression formats. While paper feeding and scanning can be done automatically and quickly, preparation and indexing are necessary and require much work by humans. Preparation involves manually inspecting the papers to be scanned and making sure that they are in order, unfolded, without staples or anything else that might jam the scanner. Additionally, some industries such as legal and medical may require documents to have Bates numbering or some other mark giving a document identification number and date time of the document scan. Indexing involves associating relevant keywords to files so that they can be retrieved by content. This process can sometimes be automated to some extent, but it often requires manual labor performed by data entry clerks. One common practice is the use of barcode recognition technology. During preparation, barcode sheets with folder names or index information are inserted into the document files, folders, and document groups. Using automatic batch scanning, the documents are saved into appropriate folders, and an index is created for integration into document management systems. A specialized form of document scanning is book scanning. Technical difficulties arise from the books usually being bound and sometimes fragile and irreplaceable, but some manufacturers have developed specialized machinery to deal with this. Often special robotic mechanisms are used to automate the page turning and scanning process. Document camera scanners. A new category of document scanner is the document camera. This does not refer to devices which are used as visual presenters, rather instead for the main purpose of document scanning. The process of capturing images on document cameras differentiates from that of flatbed and automatic document feeder scanners, in that there are no moving parts required to scan the object. Conventionally, either the illumination reflector rod inside the scanner must be moved over the document, or the document must be passed over the rod in order to produce a scan of a whole image. Document cameras capture the whole document or object in one step, usually instantly. Typically, documents are placed on a flat surface, usually the office desk, underneath the capture area of the document camera. The process of whole surface at once capturing has the benefit of increasing reaction time for the workflow of scanning. After being captured, the images are usually processed through software which may enhance the image and perform such tasks like automatically rotating, cropping and straightening them. It is not required that the documents or objects being scanned make contact with the document camera, therefore increasing flexibility of the types of documents which are able to be scanned. Objects which have previously been difficult to scan on conventional scanners are now able to be done so with one device. This includes in particular documents which are of varying sizes and shapes, stapled, in folders or bent crumpled which may get jammed in a feed scanner. Other objects include books, magazines, receipts, letters, tickets etc. No moving parts can also remove the need for maintenance, a consideration in the total cost of ownership, which includes the continuing operational costs of scanners. increased reaction time whilst scanning also has benefits in the realm of context scanning. ADF scanners, whilst very fast and very good at batch scanning, also require pre- and post-processing of the documents. Document cameras are able to be integrated directly into a workflow or process, for example a teller at a bank. The document is scanned directly in the context of the customer, in which it is to be placed or used. Reaction time is an advantage in these situations. Document cameras usually also require a small amount of space and are often portable. Whilst scanning with document cameras may have a quick reaction time, large amounts of batch scanning of even, unstapled documents is more efficient with an ADF scanner. There are challenges which face this kind of technology regarding external factors which may have influence on the scan results. The way in which these issues are resolved strongly depends on the sophistication of the product and how it deals with these issues. Infrared cleaning. Infrared cleaning is a technique used to remove the effects of dust and scratches on images scanned from film. Many modern scanners incorporate this feature. It works by scanning the film with infrared light. The dyes in typical color film emulsions are transparent to infrared light, but dust and scratches are not, and block infrared. Scanner software can use the visible and infrared information to detect scratches and process the image to much reduce their visibility, considering their position, size, shape, and surroundings. Scanner manufacturers usually have their own name attached to this technique. For example, Epson, Nikon, Microtech, and others use digital eyes, while Canon uses its own system FAIR. Plustk uses laser soft imaging ISRD. Some independent software developers design infrared cleaning tools. Other uses, flatbed scanners have been used as digital backs for large format cameras to create high-resolution digital images of static subjects. See also, barcode reader, book scanning, scintillation equipment, display resolution, gamma correction, Teal-scene, references. External links, scanner at DMOZ, is drum scanning really alive and well? From Digital Output by Jim Rich, can a fine art large format photographer find happiness with a $30,000 scanner? By Bill Glickman, Sconic, a Windows tool for sharing scanner over network. Accessed on December 3, 2011.